Relative product and composition. Given relations R1 and R2 in this order, the relative product of these relations is denoted as R1 semicolon R2. And it is defined as a relation consisting of pairs AC, such that there exists B for which A is related to B by the first relation and B is related to C by the second relation. This means we are considering arrangements of three items, A, B, and C, such that A and B are related by the first relation, B and C are related by the second relation. Whenever we can find such an arrangement, we extract A and C, and the ordered pair AC belongs to the relative product. The relation composition of R1 and R2 is defined in exactly the same way. However, it is denoted R2 circle R1. So the relative product of R1 and R2 is exactly the same as the relation composition of R1 and R2, but they are denoted differently. R1 semicolon R2 for the relative product, and in this way for the relation composition. When you see the notation for the relation composition, it is common to read it from the right to the left. You will say R1 composed with R2. That's actually the only correct reading of this notation. So the following conditions are equivalent. X and Z are related by the relative product of R1 and R2. X and Z are related by the relation composition of R1 and R2. Please notice that the only way to say it correctly is the relation composition of R1 and R2 in this order. In the notation, we have R1 composed with R2, and the order of the relations becomes different when you scan the expression from the left to the right. And these conditions are equivalent to this. There exists Y such that X is related to Y by the first relation and Y is related to Z by the second relation. Here is an example. We'll take R1 consisting of these pairs, and please notice that we have here a range domain to range diagram. Pair 1, 2 is represented by the link from 1 to 2. Pair 4, 4 is represented by a link from 4 to 4. And we are also taking a relation R2 consisting of these pairs. The middle part of the diagram and the rightmost part of the diagram serve as the domain to range diagram representing R2. For instance, 1 is related to 1 is represented by this link. And now we'll find the relative product of R1 and R2. And the question here is, how can we travel from an item in the leftmost oval to an item in the rightmost oval using the links for these two relations? And it's clear that we can travel from 1 to 4 via 2. We can travel from 2 to 4 via 2, from 2 to 2, and then from 2 to 4. And exploring such connections gives us this result. The links which play an essential role in forming the relative product have been marked as thick lines. Here's an exercise for you. Make a diagram to show R2 relative product R1. So a relative product of the same relations, but in the opposite order. After you do that, notice that the resulting relation is different from the one in the example above. In this way, you will prove that a relative product is not commutative, or expressed, which can be also expressed as a relation composition is not commutative. So please pause the video and do this exercise. Here's an informal example. The relation is a grandson of is the same as the relation composition of is a son of and is a child of. Indeed, a grandson, or maybe I should say A is a grandson of C if A is a son of B and B is a child of C. The same can be written as is a grandson of is a relation composition is a son of composed with is a child of. Here's an exercise for you. Express the relation is a great-grandmother of using two relative product operations. And then write it also using two relation composition operations. Please notice that in the example we used just a single relative product operation. When you do the exercise, you're expected to have three relations combined using the relative product. Here's another example which shows possible uses of the concept of relative product. Think that X is a set of cities, and we'll have two binary relations on X, denoted by T and F. X is related to Y by T if and only if there is a train from X to Y, and X is related to Y by F if there is a flight from X to Y. For such relations, the relative product F, relative product T, describes the trips consisting of one flight followed by one train trip. Indeed, X is related to Z by such a relative product if and only if there exists a Y such that there is a flight from X to Y and a train from Y to Z. An exercise: express the trips consisting of 2 flights followed by a train trip using 2 relative products. And then write the same using relation compositions. Please pause the video and do the exercise. More exercises. Let R be any relation on X. Complete the following equalities. The empty relation relative product R. The identity relation relative product R. The total relation on X, total binary relation on X, relative product R. Also, as a repetition, disprove that relative product is commutative. Disprove that relation composition is commutative. However, notice that we have the following proposition. The relative product is associative. When you have a relative product of 3 relations, the placement of parentheses does not matter. And of course, similarly for relation composition. And because of the associativity, we can omit parentheses and write R1 relative product R2 relative product R3 without any parentheses. And similarly for relation compositions. Please pause the video and do the exercises. One more exercise. Disprove the following equality. The inverse relation to R1 relative product R2 is the relative product of the inverse relation to R1 and the inverse relation to R2. However, it turns out that we can form the following proposition. The inverse relation to R1 relative product R2 is the relative product of the inverse relation to R2 and the inverse relation to R1. So, looking at the exercise above, if we try to keep the relations R1 and R2 on the right hand side of the equality in the same order as on the left hand side of the equality, things do not work. You need to switch the order. R2 needs to come first, R1 needs to be second. Here's the proof. Take any z and x such that z is related to x by means of the inverse relation to R1 relative product R2. So we are taking z and x which are related by this relation. Our goal will be to show that z and x are related by this relation, and this is what we hope to obtain at the end of the proof, and we'll be forming a chain of equivalences, so that we'll see that the first condition is equivalent to the last. By the definition of the inverse relation, this is equivalent to stating that x and z are related by the relative product of R1 and R2. By the definition of the relative product, this is equivalent to stating that there exists a y such that x is related to y by the first relation, and y is related to z by the second relation. Now, please compare this with the previous expression. Now, looking at this, or actually looking at this statement, by the definition of inverse relations, this is equivalent to saying that there exists a y such that y, such that that y is related to x by the inverse to the first relation, and z is related to y by the inverse to the second relation. And finally, by the definition of the relative product, this is equivalent to saying that z and x are related by the relative product of the inverse relations, where the inverse to R2 comes first in the relative product, and the inverse to R1 comes second in the relative product.